We are talking today about power supply solutions and on top of that about products which already contain these solutions. So we are not talking about the dream which is coming up somewhere, something fancy in the future. We have implemented our new technologies in a product called Q14, which we see there. It's a product which can deliver 14 kilowatts output power under very special conditions you will see in a very short time. Why did we do that? This is my starting grid for the whole day. As you have some problems in Australia, we found them everywhere in the world with mains. And there's a lot of speculation going on. Is that voltage, are there voltage spikes or power voltage drops, or what is it? And I can clearly tell you it is not related to all this what you may think. So here we see the result. It's a cut drawing, a 3D cut drawing of a power supply which is in that amplifier. Even that it looks that it could be a product in the future, it's already existing. I start with some questions to you. Are you aware that mains, of course, mostly are limited to 16 ampere breakers, and this is resulting in maximum 4 kilowatts? So it's a simple mathematical calculation, 16 amperes, 230 volt. You're ending up roughly, if you have a fantastic amplifier with the highest efficiency, at maximum 4 kilowatts. So then you are looking at the amplifier manufacturers, like us, like our competition, very good competition also, very good companies. Why are they going to announce amplifiers which can do 10 kilowatts, 14 kilowatts, 20 kilowatts? Where's the magic? The magic is simple. We can deliver this amount of power only in over a certain time until the capacity of the amplifier, the storage, is finished, and then we have to refill the storage. And with music, as this is dynamic, normally you have enough time to fill the storage of the amplifier, and then you can release the power to the output stages of the amplifier where you have music. And this can also create some big trouble on the breakers, because if you are going to draw a little bit too much current, this means the breaker would trip, then the show is over, or you have to run to the breakers, and nobody likes to do that. Obviously, it's not a good idea. Therefore, we simulate the breakers. So we know exactly when the breaker will fail because of too much current draw, or if the breaker even gets too hot. So in modern products nowadays, like we provide, this breaker simulation is included in all our amplifiers, and if it is a little bit more advanced like ours, you can even select the type of breaker. So we are always at the limit of everything to provide this power. Otherwise, it's just not possible. It's a 50 cycles, like it's announced, the amplifier runs on 50 or 60 cycles, 230, 115 volts, whatever. And you expect that this is a sine wave, a very nice shape. It's all not the case. And I show you a couple of examples what we find in field. And you must be aware that what you see now is not something special. It's just day by day. Dropouts causing, just a dropout of 20 milliseconds. This is causing, normally, with the products are not designed correctly, a reboot. So maybe 20 seconds, no sound. This can be buffered with desks, for example, with an uninterruptible power supply, UPS. But as soon as it's coming to amplifiers, there's so much current. Buffering that via UPSs is a quite big challenge and is costing enormous amounts of money. Now we see phase shifts. That's quite a challenge for any digital power supply, and in fact it is quite dangerous also. So it's easy this can easily cause even power supplies to be destroyed. If that is happening at specific parts in the waveform, this can cause semiconductors to switch too much, and they don't like it and just break. The biggest challenge in our industry, in life industry, is something you see here. So normally you expect a 50 cycle sine wave on the mains, right? And here we see what the generator is providing under normal use. So this is a very big generator, a container-sized generator, good brand. And I can tell you that this curve here is not special. This is normal. And there are very good reasons why this is normal. Generators contain a motor, an engine. And as soon as you are doing a dynamic current draw, within this current draw, the engine tries to keep up providing the current, but there's a huge latency on the motor, of course, so it cannot do it. All generators, even the big power plants, are not designed to provide power for dynamic draw. They are designed to provide continuous current. But we are dealing with music, so it's dynamic, first of all, and then in your shows you have something like, for example, hoists, and they may start maybe 20 at the same time doing something at the show, and when they start, there's a big torque, and they create a dramatic power draw, a current draw. And these current draws, we found out, can even cause oscillating on the mains at 15 kilohertz. And 15 kilohertz oscillation on the mains can be the death of semiconductors immediately. So we have had all these experiences in the past, and we provided bug fixes or upgrades in our amplifiers in order that they can cope with that specific problem. And when we designed the power supply, we said, okay, how many other specific problems can we see? What is it? Well, it's unpredictable. So because of the danger, the risks of reliability, we said, okay, it's unpredictable. Whatever it is, it can look like much more worse than this. It can look better. We are going to implement a DSP in the power supply. DSPs can deal with waveforms and look at the whole thing like analyze what it is and not speculating what kind of errors can come up. So we are solving the problem at the root cause with the DSP. It has an integrated mains analyzer, and we are following up the mains frequency, waveform and voltage in real time. This means we just don't care what it is. This doesn't matter anymore. So whatever fancy things are coming up in the future, dangerous ones or just bad ones, we just take what it is. This amplifier can eat more or less everything. And we take all energy, what is left in any waveform on the mains. That's very important because we want to have power. However bad the mains are, we want to have power. We want to have a nice concert and no more drops anymore in terms of the output power. So I show you now the solution, how the system works. This is a typical, very easy to do waveform for any power supply worldwide. In our lab, you have 50 cycle sine wave. This is the yellow curve. And the purple curve is how our power supply reacts on that mains frequency. In all the next pictures, you will see the same. The difference, what you see here, is only that you can see better if they are matching or not. In fact, they are more or less 100% identical. And everything below the waveform, of course, that's energy which we want to have to feed the amplifier to provide output power. So everything, always what we can get out of this, we can convert into output power. Now we see another example, trapezoidal waveform. This can be already quite dangerous for existing power supplies, but it's from the lab, it's not a signal you have normally. So it reacts quite easy to it. It follows up, just take what it is. Now we see that with a triangular waveform. It's the same story, it can do it. And we come back now to the page we have seen before. This is a bit more tricky to explain. All these little drops over here, whatever it is energy. And all these energies we can take as we follow up. If we would like to match them by getting rid of the offset in the picture, you can see it's more or less 100% matching in real time what the waveform, the given waveform is. So this is a big advantage as we can draw any energy left, whatever is in the waveform. This can end up providing you some 3 to 6 dB more output power. So it's not a little bit, it's just really, really big. And when we was there trying to prove our concept, we said, okay, let's create some funny curves, not just lab. Make something which is very special. So we modulated music on the waveform. And as you can see, the power supply just doesn't care what it is. Even with modulated music on the mains, it just eats whatever is there. So we could say, whatever it is, it just take what it is. And this has two very huge advantages, and it is changing a lot of things in our industry. First, we take the energy. Second, we are safe because we know what the waveform is. We can react on it. And this product is insensitive to any mains problems. And all the speculation in the past about, in Australia, for example, as we are here, it is related to power spikes or voltage spikes or whatever. I can clearly tell you it's not. Technologies to save your product to not get blown up by voltage spikes is easy. It's easy. It's not a problem. It is really related to the mains frequency, the waveforms, which can be potentially dangerous. And there's nothing we can do about it. It's just as simple as that. We can make either a bug fix, switch off the amplifier if we recognize something like that, or we just deal with it, like this solution. I'm a big fan of green energy. I love it. It's maybe the only way to save our planet on a very long term. At the same time, it says that you have energy when the sun shines or when the wind blows. But it is not necessarily the case that the concept is exactly at this timing. And so you have many decentralized mains networks in the future, in the next couple of decades, which will make the problem worse. That's clear. It will not create a better stability on the mains. So I'm afraid to tell you that many concerts which are running right now are running just because we are all lucky. By the way, errors you might have had in the past, temporary errors sent back to the factory. At a show, it switched off, couldn't switch it on again. You go home with it in your factory, you switch it on, everything is fine. Your supplier cannot find anything. All these errors, not all of them, but Many errors of them are strictly related to this problem. And yeah, therefore we thought we have to do something groundbreaking. As this product has an integrated DSP looking at the mains in real time all the time, it has some very nice facilities also. We can use it as a measurement equipment also. So here we see actually the mains which we have here, the normal mains. That's quite pretty normal behavior which we are seeing here. The software coming with the amplifier is also showing you different other aspects like power consumption, net frequency where we are right now, shows you the current draw at the moment. It shows you the output rails, which are quite high with this amplifier. It's extremely powerful, 180 volts at the output. It's pretty constant all the time. Now we give the amplifier a little bit power. We just start with the voltage graph. So just a little bit of power. There's no problem with the mains voltage. So we give it a little bit more. And suddenly you see, even on the mains, which are pretty stable here, we get some influence. And the more we give it, now we are bringing the amplifier to clipping. You see we have already voltage drops which are going down to 215 volts or 210 volts, 200 volts. And depending on how many amplifiers you are now connecting to the same network, you can imagine that the impact is getting higher. That's it's a simple scenario. Amplifier heats up a little bit, as we see. So we are down below 200 volts already. But this is not a problem for the amplifier. This is not a problem for the mains, not for the amplifier. It's just a standard behavior, and I think it's very useful for you to get a little bit insight of what that all means. We have to go to the limits of the mains, otherwise it's not possible to provide this power. Also, we look now to the simulation of the fuse. When I pushed the system, the fuse was going and having only 30% headroom in terms of heat and maximum current draw. So you can imagine, now the fuse is cooling and we can get back to it. And also, with a crazy signal, we are of course able to, or should be able, depending on the crest factor of the signal, to heat the fuse so much up that we are going to fuse protection. And as you can see, we are at the limit of the fuse with full output power all the time. And we are safe here, so the light is still on, is stably working, right? But still, and again, this is a quite easy thing for technology. Now, let's go and simulate a case which is a problem. So I show you something. We have prepared, this in fact is a generator, a baby generator, 2.5 kilowatts. So now, let's see what happened. You can look to the video also, which is interesting. And I invite you in in 1 or 2 minutes to go there actually and have a look how this little generator is reacting to this amplifier, which is not necessarily and definitely not the case with a container one, but the principle of reaction is the same. So you get an idea how the engine is working and whatever, what is happening in bigger environments. Not really exactly so much, but the same thing in principle. We start now with pushing the system, and I can tell you we are already at we are below 60 volts. The point is, even that this is extreme, and we of course are very proud to show you that our product can deal with it. This is one part of the story. But there's no definition how extreme it can be that other products will still work. There's no definition. Or let's say there's a definition plus minus 10% in voltage. I wouldn't rely on that one. So it's important to understand there's a potential risk for any other connected unit. They may react like the lamp we see here, or may already switch off, or temporarily switch off and come back, and you send it back to this factory and say there's an error because you are not aware about this situation. So therefore I clearly tell you it's extremely important that you buffer equipment as much as you can in live applications with UPS, and look to new technologies to buy for high current devices like amplification.